I'm Dr. Shanthi, working as Associate Professor in Department of Electronics and Telecommunication Engineering, RV College of Engineering. We recently conducted a workshop from our department along with Sage and Keysight. As a part of the workshop, we designed an amplifier which works at 5G frequency of 3.4 GHz. It's a one-of-the-kind of workshop because in this workshop, we designed the amplifier, we simulated, we did the layout, and again EM simulation is performed. We fabricated, finally we tested the PCB also. And now I'm going to show you how this amplifier design, whichever we fabricated and got it, can be tested with our facility, vector network analyzer in our lab. Okay, now we'll start with the experimentation of the board what we have fabricated. So for the testing first, I have to go for first calibrate the vector network analyzer what we are using. Our vector network analyzer is varying from the frequency range of 9 kHz to 6 GHz. And the thing what I'm having in my hand is nothing but the calibration kit. So with this calibration kit, first I have to calibrate the VNA before I start with doing any measurements. I have to bring down all the ports of the VNA to the reference level and we have to start the measurement. So that's the first process we have to do now. So I'll be starting the calibration process. Okay, so now I have connected the calibration kit. In this calibration kit, there are 4 ports. You have a short, open, matched and through. These are the 4 ports. So I have to connect every channel, port 1 and port 2 of VNAs to all these ports and verify whether I am bringing the reference value to 0 and I start my measurement. So after calibrating the port 1, we do the same procedure for port 2 also. And once after verifying all the ports open, short and matched and seeing the value same as the port 1, like you will be getting 0 dB for short and open also is 0 dB, and for matched it will be very low like minus 40 dB kind of thing, and that is verified once. Then the calibration and throughput also has been done. Once after doing all these things, the calibration is done for the VNA, and now we are ready to start our testing. So now we'll start the measurement exactly. So we'll be using these 3 things for the measurement. This is a board which has been fabricated as a outcome of the phase 1 workshop. So this is basically a 3.4 GHz 5G amplifier. The transistor here what we use is nothing but a gallium arsenide FET, and the whole circuit is done on the FR4 substrate whose dielectric constant is 4.4, and all the matching circuits here is nothing but the microstrip matching circuits, and we have some chip resistor and chip capacitor used. The chip resistor is nothing but one resistor which we have added on the input side in order to improve the stability. And other than that, we have so many chip capacitors. The chip capacitors, we have 4 chip capacitors on the biasing circuit and 1 chip capacitor on the input side. The other one is the output side, 1 chip capacitor we have. The values of chip capacitors are 2400 picofarads. And when I come to this one, it's nothing but a dual power supply. Here this transistor is going to operate with a maximum VDS of 3 volts and VGS of minus 3 volts and VDS of plus 4 volts. So I'm going to use here a dual power supply whose range is far more greater than that, and the other one is nothing but the VNA. So what I have done here is before going to connect the biasing voltages to the board, I'll be first terminating this amplifier circuit, the ports with the matched load. To be on safer side, I terminate both the ends. I cannot leave the ends open and I cannot give the bias voltage. It will pick up some transients and it may damage the transistor. So first I go for connecting the matched loads on both the ports, port 1 and port 2 of the transistor board, and then I'm going to now connect this to the biasing voltage. This side is nothing but my input VGS and the other one is the VGS. So before connecting this, I'll go and set the VGS value, a greater value, to be safer. I set this VGS to around minus 1 volts. I have set the VGS, and if I check the VDS, I have kept VDS 0. So I'll just keep it the VGS as that, and I'll apply the VGS first to my circuit. So my input side is VGS, so I'm giving this to the minus terminal of this power supply. Negative terminal I'm connecting to VGS, and positive terminal I'm connecting to the VDS. Drain side, I'm connecting the drain side to the VDS. So after completing this is the one important thing, I have to ground the board. Okay, without grounding it will not work. So I'll be grounding the board either to the substrate or to the terminals here, or I can go to the connector pads. I can ground it at any point. So this is a setup what we will complete first, and then I'll go for taking my positive voltage. So slowly I will start to increase my positive voltage to 3 volts. I'm choosing a VDS value of 3 volts, and I'll come back to VGS. Still my VGS is in 1 volt, so there is no current showing here. So I'm going to operate this transistor at a bias current of 20 milliamps. So what I will do, I'll slowly start to decrease this. I'll go to the second option here. I'll slowly decrease this to some 0.7 something. I'll check what is my VDS. Still there is no current drawn. I'll go back to VGS. Again slowly I'll decrease and come. At one point of time it will pick up some current. So you see, you can observe here at 3 volts VDS I'm having 28 milliamps, but still I have to bring it down to 20 milliamps. So I'll little bit increase this and check if it's increasing. So what I will do, I'll just little bit increase this value to 0.5. I'll observe, yeah, now it's coming to 20 milliamps. So this is a perfect condition what I have set now. So my VDS is 3 volts and ID is 20 milliamps and VGS is minus 0.5 volts. So this is a perfect condition for my amplifier to operate. So once after setting all these things, now what I will do, I will remove this first, my output port. I will connect this to my port 2. Okay, I'm going to observe the outputs actually in VNA, so I can connect this to. After connecting the ports, exact ports to VNA, this values will definitely change again. So again we need to set. Okay, to be on safer side, I'll increase this to -1 and then I'll work. Later I'll bring back to the actual value. Okay, so now I've connected my output side, and input side I should not connect it immediately. I have to connect the RF input. I'm applying the RF input to the board. That should be applied in the last stage. You should not apply it in the beginning itself. So after complete connecting the port 2 to the port 2 of VNA to this one, I'm connecting to input side. We have connected the port 1 and port 2 of the VNA to amplifiers port 1 and port 2. So we are going to observe the S21 parameter. So we can observe here the S21 as 3.4 GHz. We are able to get the gain of 10 dB. So here what is the gate voltage is set as minus 0.06 voltage. I can just go for increasing this. So if you increase this, you can able to see the variation in the gain. So the gain is changing now. If I change the gate voltage, if I increase the gate voltage, I can observe the change in the gain. So the gain is increasing, and then it comes to, it's going to 9.9. It is in the same range. If I want to still get a better gain, I'm increasing my gate to source voltage. So I'm bringing down to a voltage value of minus 0.0706. So this is my final value with which I retain a gain of 10 dB. So if I observe what is a VDS, the VDS is fixed to 3 volts. So you can get a gain of 10 dB for this amplifier, which is appreciable. The actual gain will be around 16 to 17 dB as per the data sheet. So now I go for observing the other parameters also. If I check the S11, S11 also is minus 12.54, and if I check the S22 or 3.4 GHz is minus 10. So you are able to get the gain of 11 dB, S1 of minus 10 dB and S22 of minus 10 dB again. So I can add the trace and get all the values in the same window. So you can add the trace. I'll show you how to plot all the graphs together here. So this one I'll change it to S22. So I'm able to see all the 3 graphs here. All the 3 graphs, one is S11, other one is S22, the next one is S21. So if I place a marker, I can place a marker for everything, and I can just vary the marker at 3.4 GHz. So I am moving the marker 2 I am moving, it is going to 3.4. At 3.4 GHz I am able to observe minus 10 dB. This is nothing but S22. Similarly, at marker 1 also, already we have set at marker 1 as minus 10 dB, and we'll check for the gain S21. So for the gain S21, if I place a marker, this marker 3.4 if I am keeping, if I keep at 3.4, the blue one I am moving now, it's 3.4. If I keep, it's showing me as it's 10 dB. So the gain is also 10 dB. Your S11 also is minus 10 dB, your S22 also is minus 10 dB. So totally we have 3 graphs here. Even we can plot the S21 also, S12 also. So I'll go to add trace. This one I'll change it to S12. So your S12 will be basically a very lower value. So you can have a marker at 3.4. Even this value is also very much low, around minus 40 dB it's coming. So you can go to trace. From the trace you can, in this trace only you can see, you can import or export the data. I'll go for export the data. So I'll be saving this data, and you can save this as a S2P file, or you can save it as a .csv file, or you can save it as a MATLAB file, and you can go and open this S2P file into a 2-port network in ADS and can plot all these graphs and compare with the simulation results.